Good morning, students. Most welcome in the chemistry class with the chapter Classification of Elements and Periodicity in the Properties. Today we are present with the topic Shielding Effect. My dear students, you know that shielding effect. What is the application of the shielding effect? Students, you know, in multi-electron atoms, the electrons are present in the outermost shell and they don't experience the full positive charge. Hence, they are shielded or screened away from the nucleus. The electrons present in the valence shell, they experience two types of the force. One is the attractive force, that is by the nucleus, and second is the repulsive force that is created by the inner shell electrons. So the electrons present in the valence shell experience the two types of force. One is the attractive force, another is the repulsive force. For example, in the same subshell, the p electrons will get shielded away by the s electron. Why? Because the p electron is away from the influence of the nucleus and hence it does not experience a complete positive charge. So students, hence it does not experience a complete positive charge. Now students, ionization and atomic radius are correlated in two ways. What are the two ways? First way is the attraction of the electrons towards the nucleus and the repulsion of electron from each other. The effective nuclear charge, I discussed previous day, the effective nuclear charge experienced by a valence electron in an atom will be less than the actual charge on the nucleus because of shielding or screening of the valency electrons from the nucleus by the intervening core electrons. So students, the attraction by the nucleus to the valence shell electrons is reduced by the repulsive force from the inner shell electrons. So the net effect of the two forces, one is the attractive force, this is the nucleus, positively charged nucleus, and electrons of interest and electrons between electrons of interest and nucleus cancel. So the attractive force by the nucleus to the outermost electrons will be reduced due to the screening or shielding effect of the inner shell. So students, what I am telling you, the two effects experienced by the valence shell electrons. One from the nucleus, another from the inner shell electrons. Inner shell electrons and the valence shell electrons charge equal, so there is the repulsion. And this repulsive force reduces the attractive force from the positively charged nucleus to the valence shell electrons. So there is the shielding effect that is created by the inner shell. And my dear students, the shielding effect of s orbital electron is more than p orbital, than d orbital, than f orbital, because the s orbitals are nearer to the nucleus. Now there are some anomalies. Anomalies are there. 2s electron of lithium is shielded away by the 1s electron because the atomic number of lithium 3 electronic configuration 1s2 2s1. So 2s1 electron of the valence electron, my dear children. So this 2s1 electron, that is experience the shielding effect from the 1s electron. The 2s electron lithium is shielded from the nucleus by the inner core of 1s electron. As a result, what is happening? The valence electron experience a net positive charge which is less than the actual charge of plus 3. So, in general, shielding is effective when the orbital in the inner shell are completely filled. This line is very, very important. In general, shielding is effective when the orbitals in the inner shell are completely filled. This situation occurs in the case of alkali metals, which have single outermost ns electron. As per example in sodium, 1s2, 2s2, 2p6, 3s1. So these 3s1 electrons preceded by a noble gas configuration. In the case of alkali metal, which have single outermost ns electron, so preceded by a noble gas electronic configuration by losing one electron. My dear children, when we move from lithium to fluorine, fluorine atomic number 9, 1s2, 2s2, 2p5 electronic configuration, across the second period, successive electrons are added to orbitals in the same principal quantum level. So cell number is not increased, but electron number is increased. And the shielding of the nuclear charge by the inner core of electrons does not increase very much to compensate for the increased attraction of the electrons to the nucleus. So this is very, very important. On moving, that is when we move from left to right, the cell number not increased, but electron number is increasing in the same principal quantum level. Thus, across a period, increasing nuclear charge outweighs the shielding. Consequently, what is happening here? The outermost electrons are held more and more tightly, and the ionization enthalpy increases across the period. So, you can explain the ionization enthalpy across the period. Why increasing? Why increasing? Already I have discussed this, students. Now, what is when we move from top to bottom, what is happening there? The outermost electrons being increasingly further from the nucleus because their cell number is increased. There is an increased shielding of the nuclear charge by the electrons in the inner levels. In this case, what is happening here? Increase in shielding outweighs the increasing nuclear charge, and the removal of the outermost electrons requires less down a group. That's why we can explain the ionization enthalpy on moving down the group decreases. On moving down the group decreases because increase in the shielding outweigh. My dear children, it is easier to remove 2p electrons of boron than 2s electron of beryllium. The first ionization enthalpy of boron is slightly less than beryllium. Why? Though the former has the greater nuclear charge, when we consider the same principal quantum level, an s electron is attracted to the nucleus more than the p electron. In beryllium, what is happening, my dear children? In beryllium, the electrons removed during the ionization is an s electron, whereas the electron removed during ionization of boron is p electron. So, in case of beryllium, s electron is removed. In case of boron, p electron is removed. The penetration of the 2s electron to the nucleus is more than that of the 2p electrons because 2s electron nearer from the nucleus than 2p electron. Hence, the 2p electron of boron is more shielded from the nucleus by the inner core of electrons than the 2s electrons of beryllium. That's why it is easier to remove the 2p electron from boron compared to removal of the 2s electron from beryllium. Thus, boron has a smaller first ionization enthalpy than beryllium. It is very important questions for the exam. Why boron has the first ionization enthalpy, has a smaller first ionization enthalpy than beryllium. So you can explain from this. Now you can explain first ionization enthalpy of oxygen is less than nitrogen. Why oxygen first ionization enthalpy is less than nitrogen? So I will explain now. The smaller first ionization enthalpy of oxygen compared to nitrogen. This arises because in nitrogen atom 3 2p electrons reside in different atomic orbitals, whereas in oxygen atoms 2 of the 4 2p electrons must occupy same 2p orbital, resulting in an increased electron-electron repulsion. Students, you know, in case of nitrogen, what is the electronic configuration? 1s2, 2s2, 2p3. And these 3 electrons are distributed in the degenerate p orbital, px orbital having 1 electron, py orbital having 1 electron, pz orbital having 1 electron. But in case of oxygen, what is the electronic configuration, my dear children? 1s2, 2s2 and 2p4. So these 2p4 electrons are distributed like as 2px2, 2py1 and 2pz1. So in the oxygen atom, 2 of the 4 2p orbitals must occupy the same 2p orbitals, 2, 1, 1. And consequently, it is easier to remove the fourth 2p electrons from oxygen than it is to remove one of the 3p orbitals from nitrogen. Nitrogen p3 orbitals, half fill orbital is more stable than p4 configuration. So it is easier to remove the electrons from the 2px2 for oxygen, and it is difficult to release the electron from p orbital of nitrogen because there is a half filled orbital. That's why the ionization enthalpy of oxygen. So ionization enthalpy, what is the question? What was the questions there? Ionization enthalpy of oxygen is less than the nitrogen. So what is the conclusion of this? Nitrogen has a half filled orbital, p3, so it is difficult to release from the half filled orbital because you know, my dear children, half filled and full filled orbitals are very stable. So ionization enthalpy of oxygen is less than nitrogen. This is very important questions. Now give reason why are lanthanoids, actinoids placed and elements like zinc, palladium, cadmium are not considered transition elements because they have the D10 configuration, that is completely filled d orbitals. While lanthanoids, actinoids placed separately at the bottom of the periodic table for convenience and systematic study of elements having similar properties, and to maintain the structure of periodic table of classification by keeping elements with similar properties in a similar way. Elements like zinc, palladium, cadmium are not considered the transition elements as they have filled d orbitals. Chemistry of actinoids is completed. Why chemistry of actinoids is completed, students? As they show large number of oxidation state than lanthanoid series. Now students, ionization enthalpy is completed. Next is electron gain enthalpy. I have discussed already about this. What is electron gain enthalpy? When an isolated gaseous atoms accept the electrons, it forms the anions, and for this energy will be released. Sometimes energy will be needed also. When the energy will be released, when the energy will be needed, that depends upon the systematic configuration of the elements. As for examples, electron gain enthalpy definition you should know. When an electron is added to a neutral gaseous atom to convert it into a negative ion, the enthalpy change accompanying the process is defined as the electron gain enthalpy. Electron gain enthalpy provides a measure of the ease with which an atom adds an electrons to form anions. As for examples, Xg plus E minus X minus G. Depending on the elements, the process of adding electrons to the atoms can be either endothermic or exothermic. When electrons added and anion is formed, as for example oxygen accept the electrons and form O minus, and then energy is released. When the atoms, gaseous atoms, has the tendency to accept the electrons more To achieve the electronic configurations of inert gas or stable electronic configuration, then it will release the energy. Then it will be exothermic reaction. As for example, inert gas has the completely filled outermost shell. So it has no tendency to take the electron. So when electron is added to the inert gas, then the energy will be needed, not energy will be released. And this time the enthalpy change on adding the electron will be the endothermic, my dear children. So added to atoms and electrons added to the atom, and the electrons gain enthalpy is negative. For example, group 17 has the negative electron gain enthalpy. On the other hand, noble gases, just now I told you, noble gas has no tendency to take the electrons. But if electron is added to noble gas, so energy will be needed. So this will be the positive electron gain enthalpy. This will be positive electron gain enthalpy. As a general rule, electron gain enthalpy become more negative with increase in the atomic number across a period. When we move in the periodic table from left to right, what is happening here? That is, electron gain enthalpy will be more negative. That is, more energy will be released on addition of electron. The effective nuclear charge increases from left to right across a period. Already we have discussed, my dear children, and consequently it will be easier to add an electron to a smaller atom, since the added electron on an average would be closer to the positively charged nucleus. Now students, we should also expect electron gain enthalpy to become less negative as we go down a group. Why? When we move from top to bottom, the electron gain enthalpy will be less negative. Why? Because when we go down a group, the size of the atoms will be increased and the added electrons would be further from the nucleus. So this is about the electron gain enthalpy. And what is electron gain enthalpy? The enthalpy which is released or needed to add the electron to an isolated gaseous atom. Along the period, electron gain enthalpy becomes highly negative, that is, more energy will be released. But when we move from top to bottom, electron gain enthalpy becomes less negative, that is, less amount of energy will be released. Now, what is electronegativity, my dear children? This is the physical properties of the elements. Electronegativity is the ability to attract the shared pair of electrons towards the more electronegative bonded atom. A qualitative measure of the ability of an atom in a chemical compound to attract shared electrons to itself is called the electronegativity. My dear children, fluorine has the highest of electronegativity value 4. It is the most electronegative element. So which is the most electronegative element? So fluorine is the most electronegative element. In the Pauling scale, it is measured, its value is 4. Non-metal elements have strong tendency to gain electrons. So from left to right, the electron negativity will be increased, and on moving down the group, electronegativity will be decreased. It can further extend to say that the electronegativity is inversely related to the metallic properties of the elements. Thus, the increase in electronegativities across a period is accompanied by an increase in non-metallic properties. Suppose electronegativity increases, it means that non-metallic character increases. Electronegativity decreases and electropositivity increases, then metallic character, my dear children, will be increased. The decrease in electronegativity down a group, it means decrease in the non-metallic properties. So, students, I have discussed about the atomic radius, ionic radius, ionization enthalpies, electron gain enthalpies, and electronegativity, their definition and their changes along the period and moving down the group. Students, up to this, next day we will come with the new topics of this chapter. So students, good day and take care of you. Bye.